this class will be about the Poisson process, about the Poisson distribution, and their relationship to the exponential distribution. And just making sure that you understand that this Poisson process is very important for the Markov chain stuff that we're going to be doing in the next chapter. All right, so let's define what a Poisson process is. So a stochastic process in t with t greater than 0, greater than or equal to 0, is said to be a counting process if n of t represents the total number of events that occur up to time t. All right, so that's a counting process. And then, so one of the most important, but I'm going to put the most important, at least for our class, the most important counting process is known as the Poisson. Just like I said in the beginning of this, Poisson process, which is defined as follows, counting process n of t greater than or equal to 0 is said to be a Poisson process having rate of alpha. Alpha is greater than or equal to 0. Not greater than or equal to. It's just greater than 0 if these three things are true. Number one, n of 0 is equal to 0. 2, the process has independent increments. It's an n, independent increments. And 3, the total number of events in any interval of length t is Poisson, believe it or not, is Poisson distributed with mean. So there's only one parameter for the Poisson distribution, and it's the mean parameter, with mean equal to alpha t. And we'll see a couple of examples of this. So what do these really mean here? So the counting process. So this is just saying the counting process begins when t is equal to 0. So there's not any extra numbers in there. This requirement can be verified. So this can be verified by our knowledge the final thing down here, let's go down a little bit. So what we're talking about here is the probability of n t plus s minus n of t is equal to n is equal to the Poisson distribution. So, and we'll see this several times throughout the course of this, but it's e to the mean, which in this case is alpha t, and then the mean, alpha t, the only parameter for this distribution, to the n power, all divided by n factorial. So the probability that you get n occurrences or events in that little time period t, the probability of that is equal to this, it's distributed this way, which is a Poisson distribution. So let me just write out or draw a little picture here what that looks like or what we're talking about. So if we have this as s, right, and this is s plus t, right, so, or t plus s, whichever way you want to write this, it means the same thing, minus the number, so the number that are in between this interval, in other words, this interval in here is Poisson distributed, and it, again, it doesn't, so there's 4 in here, but really the idea is if I want to know the probability that I get a certain number of events where x is an event occurred on this number, on this timeline here. So in this case it's 4, but it could be, it's random, or how many is going to occur in there. Then this piece here, this is a length of t, because s plus t minus s, and then this would be n of t, the number of occurrences that occur in there is that. So another way of looking at this is to define this random variable x as the number of events that occur in time interval t. And then what we're saying is that the random variable x is going to be distributed as a Poisson, and the only parameter that I need for the Poisson distribution, so the only parameter that I need for this Poisson distribution is my alpha t, which is my mean. So come down here and say it's alpha, so it's alpha t, which is our only parameter. Which means the mean is equal to the rate times time. And the probability that x is equal to, so I'm changing this now from an n, so I made it into a random variable here, and then I'm going to put it in here as, just like we do random variables, I'm going to say random, some small x is equal to, but it's going to be the same distribution, so it's e to the negative alpha t to the x now instead of n, all divided by x factorial. So anytime we're looking for the Poisson distribution and we know the parameters alpha t, then this, and I'm looking for a probability of some particular number here, then this is what it turns out to be. Okay, so what does that look like in terms of, so I'm going to come down here, put some extra space in here so I can actually give you a PMF, because this is a discrete distribution and we want to be able to put a discrete PMF in here. So what would that look like? I need a lot of room. The idea here is that you could get any number in that time period. It just so happens that it's more likely that some are going to occur more than others. But and technically, we could get an infinite number that occur in that time period. So we want to be able to have this distribution that allows for that. So we could get, so what's our support for this distribution? 0, and I gotta have a large space here. 1, another large space. 2, and I'm gonna put dot, 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 because technically we could get an infinite number that occur within this time period. Although that probably won't happen, but we have to have a distribution that allows that. So this would be P of X. It's the probability random variable X is equal to some X. And for 0, let's just remember what it looks like, or figure out what it looks like for 0. So alpha t, and then alpha t to the x power divide, not x, we know what it is, to the 0 power, we know what we want our x to be, all divided by 0 factorial. And then e to the negative alpha t to the 1, all divided by 1 factorial. And then e to the negative alpha t to the 2 over 2 factorial. And then dot, dot, dot would be basically e to the negative alpha t to the x over x factorial. So remembering what we talked about up here. So technically what I should have probably done was wrote this out and say, oh, this is the probability for 0, this is probability for 1, probability for 2. So this is the 0, probability for 0, probability for 1, probability for 2, and then what is the actual distribution for any particular x. I'll throw x up here, and then put it in. Okay, so let's see an example. So example 1 states, example 1 is customers arrive at an ice cream parlor according to the Poisson process at a rate of 2 per hour. What is the probability that no one shows between 3 p.m. and 4 p.m.? And we also want to do the PMF that covers many or much of the problem. I probably should have said many here. So change that. Many of the probabilities. What do I mean by that? Well, I mean, again, like we said just a second ago, this could go on for infinity, but it's highly unlikely that we'll get an infinite number. So we'll start off with our random variable. We'll let it be x again, and we'll state as the number of customers that visit an ice cream parlor. Oops. Let's just say parlor. Parlor between the hours between 2 p.m. and 3 p.m. So what are we talking about there? That's just, if we're going to look at this time interval, this would be 2 p.m. and 3 p.m. This time is equal to 1 hour. So we just got to make sure that this marries up with our rate. 2 per hour we would expect, right? So in 1 hour I would expect to have 2 per hour, I would expect to have 2. And that's where you're getting the mean. So we'd expect 2 per hour times 1 hour. We would expect 2 customers. But that's not what we're trying to find here. We're trying to find if nothing happens in this interval. So we're going to let x be distributed as a Poisson with 2 times 1, right? Alpha t, alpha times t. And then we're going to find the probability that x is equal to 0. So probability that x is equal to 0. So what is that? We can figure it out. It's right here. The probability that x is equal to 0 looks like this. And so it's e to the negative, this is 2, alpha times t is 2, so e to the negative 2, 2 to the 0, divided by 0 factorial. Yes, that is a 0. 0 factorial is equal to e to the negative 2, which if we put it in our calculator, we get, so because that goes to 1, this guy's 1, just left e to the negative 2, and we know that that's 0. If you put in our calculator, 0.135335. Okay. Okay, so that's the probability. Okay, so give the PMF for many of the possibilities. So let's go to R to do that. So I'm going to stop sharing, and I'm going to share our R notebook, and then we'll open up a little script here, and we can then in here. Okay, so yes, you can see that I've been looking up some of the things, and so I think it's called D. So over here you see this D Poisson. The density is what that stands for. The distribution functions. So what they mean is the cumulative distribution function, the quantile function, which is Q, and the random so if we wanted to produce random generation from that distribution, random variates from that distribution, we use R. So I'm going to use D Poisson because that I want just for one particular one. So D Poisson, we want 0 and we want lambda to be 2 times 1. And as you can see, we're getting the same number that we got before. Okay, so now what I want to do is produce many of them. We'll go sequence, I don't know, 0 to 10 maybe. Maybe 0 to 10 will capture most of this. And then probability of x is equal to D Poisson. And we'll put in each one of those x's, 2 times 1. And we'll create a little data frame that will we'll let this be x equals x. P probability of x equals round. Let's do px comma 4. So this thing is going to have really, really small numbers in it. And if I don't round them, it will give us things that maybe we're not visually as nice. And so that's why I'm doing round here. I don't even know if I need x equals x. Here's what I'm going to do. I'm going to just change that to my row names. So control enter, control enter, control enter. And then what we'll do is we'll change our rows. Row names of PMF. Print PMF. And when we do that, we get these, so really, really small number at 10, a small number at 9, although it's still registering with 4 decimal places. And so I think we've captured what we're looking for here. So I'm going to copy this and then stop sharing it and then start sharing this. And I'm going to go ahead and paste it in. Ooh, it's really small. So I'm going to highlight it and go to maybe 14. And we can move this around. So I'll move it around. All right. So as you can see, the probability of getting 0 in this window here is 0.1353. The probability of getting 1 in there would be 0.27, the probability of getting to 0.27, and so on and so forth. All right, so let's go with starting at noon. What is the expected time of getting the 6th customer? Okay, so now what we need to think about is, what does it mean to get the 6th customer and the expected time, right? So I want to start at noon or 12, and then how long should we expect to get, if 1, 2, 3, 4, 5, and then 6, to get 6 customers? So what time? All right, so if we're dealing with the expected value, we know, and this is a Poisson distribution, we know that alpha, which is 2, times my time is equal to, we want that to be equal to 6. So if we said t must be equal to 3, that's when we would expect to get our 6 customers. So we just add 3 here. So our time, our t, our window here, our interval, t is equal to 3. And let's change this to then 3 p.m. so that 12 minus p.m. So 3 minus 12 is 3 hours. Okay, so that's how we would solve that one. And then the next one asked, what is the probability that 2 or more people visit the parlor between 6 and 8? Okay, so let me draw my little window here. So this would be 6 p.m. This will be 8 p.m. Oh, and we want the PMF and the CDF. So I want to know, what is the probability of 2 or more? So how many? 3, it could be 4, it could be whatever. So we're going to let X be defined as the number of customers that enter the parlor let's see, we want to enter the parlor between, I'll go ahead, oops, I accidentally pressed a button there, between 6 p.m. and 8 p.m. T equals 2 hours. Okay, so what does that mean about X then? X must be, if it's a Poisson process, then it's Poisson 2 times 2. All right, and at this point, I just want to note what's happening here, right? So because we're dealing with a different time period here, note this. So just take a note that the parameter mu equals to 2 times 2 changed from the last problem. When it was 2 times 1, which was 2. Just take note of that. I just wanted to point this piece out, that this is important, that you understand sort of what's going on here. The fact that in the last one it was 1 hour. So in the last one we were talking about here was a 1 hour window. And then now what we're talking about is a 2 hour window. So the number of customers that come in this 2 hour window is obvious, and especially the number that we expect, or even the probabilities, are all going to be different than it would be if we're still talking about a 1 hour window, in which it should. So what we want to know is 2 or more. So 2 or more people. So that's what we're looking for. So I got to write a probability statement for that. So probability, the random variable X is 2 or more. So 2 or greater than. All right. And how can we use the CDF? Because later on we're gonna do this with the, we're gonna have to do this with the CDF. Why is that? Because X can be any number. 2 or greater means I have to keep summing this thing out to infinity. Because it is possible, even though not likely, that this thing will go to infinity. So we're going to have to do this with 1 minus the probability that the random variable x. All right, now I want to include 2 in this probability, but I don't want to. So okay, so let's think about this for a second. Let's think about what this thing looks like. So there's some probability that lies on 0. There's some probability that lies on 1. There's some probability that lies on 2. So 0, 1, 2, 3. And probably a little bit more that lies on 3. And a little bit more that lies on 4. Since I haven't calculated these probabilities, I'm not real sure what they are. But we do want to include here, so we want to 2 or greater, so greater than 2. So we do want to include all of these probabilities. So I want to include this plus this plus this. So if I'm going to write this probability statement, this has got to be less than or equal to, this has got to be less than or equal, so it's this stuff over here, so less than or equal to 1. And that's equal to 1 minus quantity probability that x is equal to 0 plus the probability that x is equal to 1. All right, and we can calculate those. Yeah, those are pretty straightforward. So the probability that we're 0 would be 4 to the 0, right? Remember, this is 4. So 4 to the 0, e to the negative 4, all over 0 factorial plus 4 to the 1, e to the negative 4 over 1 factorial, which would be 1 minus, let's see, that would be 1, and that would be 4. So 1 e to the negative 4, 4 e to the negative 4 would be 5 e to the negative 4, which, let me put it in my calculator real quick. All right, so I get 0.908422. All right, and let's go to R. Let's go to R and find out what it gives us, just to make sure that we're correct. So again, I'll stop sharing this one. I will start sharing my R notebook. And and I think it asks us for the CDF and the PDF as well. So we're going to definitely need to go to R in order to do that, because we don't want to do that by hand. So the first one is, so part C. So part C here is just 1 minus parentheses d Poisson, what is that, 0, so we wanted the 0 one, and then 4, 2 times 2, you can do 4 for that, and then plus Poisson 1 comma 4, 0.908, and it does. Another way to do that, instead of using the density, we want to use the CDF. You want to use the P Poisson. So let's do that. That would be let's see, P Poisson. So 1 minus P Poisson. And then we want to go up to 1. So probability that x is less than or equal to 1, and that's a 4. Control enter, and we get the same number. Okay, so that's all good. And then if we wanted the CDF and the PDF, we could say, well, x is equal to sequence. We'll go to from 0 to 10 again. Then P of x, d Poisson of, let's see, so be x and 4. So x and 4, and then let's see, what should we call this next one? fx. F of x is equal to the P Poisson of x, comma. then we'll let distribution equal, okay, we'll let it be called that, and then data.frame, so something that we can print off. Px, probability of x is, we'll round our px to 4 again, and then we'll let our fx round comma, we'll round to 4. And then we'll do row names again. So row names of distribution is equal to x. Distribution. And I will copy this one. Control C. And I'll stop sharing. I'll share that again. Paste. We'll make it big again. I don't know, 14 I think worked last. Oops. You gotta highlight the entire thing and then say, nah, we gotta have that sucker at 14. And then you can move that around if you want to. All right. So we see that 0.908422 is the answer that we come up with. So it would be 1 minus this number here if we were using our, or it would be 1 minus this plus 0 plus 1, right? So it would still give us 0.908, just like we saw in R. Okay. The next thing that we want to, so we're going to sort of stop business on this one. And so I will start I'm going to insert a line here just to put that we're sort of done with this Poisson process for a second. The next thing that we want to talk about is the time between occurrences in the Poisson process. So we're done talking, or at least taking you through an example, but what I'm interested in now is the time in between these two occurrences in a Poisson process. So I'm going to need me a little bit of space to do that, so I'm going to increase the next example. And the way we're going to attack that is we're just going to sort of throw up some ideas and then try to figure out what this thing is actually. And what we want to do is we want to link the exponential distribution to the Poisson process. So right now, let's just assume a Poisson process. And notice that our rate's going to be a little different with rate of lambda. So instead of alpha this time, I'm going to use lambda for a counting process. And let's let a random variable w be defined as, this is really what we're interested in, the time until the next event. Okay, what do I mean by the time until the next event? Well, what you're assuming is if w is the time until the next event, then no event has occurred for that particular point in time. So this CDF of this w random variable is equal to the probability that the random variable w is less than or equal to w. Again, we're just using the capital W to represent the random variable, and the small w is the actual time, right? So it's the variate that comes out of that. So, and this is the small w as well, the one that corresponds to the top of the PMF. or the CDF. Okay, so if this is my probability statement for this guy, this is also 1 minus the probability that W is less than or equal to, oops, not less than, we already have the less than. We want it to be is greater than or equal to W. So 1 minus this, and we don't care about the equal sign because this time until is the time until a random variable is a continuous time, so it's a continuous distribution, and the random variable W is going to be this continuous. So it doesn't matter that this is less than or equal to and this is greater than or equal to, because there is no probability at one particular point for a continuous distribution. Okay, and what does this imply here? If we are assuming the next event, right? Because so what does that mean if I'm trying to find the time until the next event? Well, that means no event. Then no event has occurred. Then no event has occurred up to that time W. All right, so nothing's occurred yet because we're letting W be the time until the next event. So that's what we're looking for. And then further, I'm going to define another random variable. Define X as the number of events that occur in time W. Okay, so what are we talking about here? What does this little window look like? So I have some time, so this time here is length of W, and our first event occurs right there. So what I want to find is the probability that nothing occurs inside this window of W. So what I'm looking for is the probability that the random variable X is equal to 0. So nothing's occurred up until that particular point when it happens. And so what's the probability that nothing occurred in that time window W? So what does that mean about my random variable X? How is it distributed? It is Poisson with W, with alpha. If you remember, it was alpha times T. In this case, alpha is lambda. So it's lambda, and our time component is W. So alpha T in this case is lambda times W. So if X is this Poisson lambda W, then I can find this probability. So how am I going to find that probability? It's just, we know because this is a Poisson process, that this is equal to lambda W to the 0 power e to the negative lambda W over zero factorial, which is equal to e to the negative lambda W. So the probability that nothing occurs in the window W tells us that that is the next event. So really this sucker here is equal to the probability that W is greater than or equal to W. All right, so all we're going to do now is, so I do have something for the probability W is greater than W using the Poisson distribution. And I'm just going to take this piece, and let me change the color. I'm going to take this thing and substitute it into here to get f of W. Because what I'm looking for is I would like to know the distribution for this random variable. And if I can find, so if we're looking for W, and if I can come over here and find the CDF for W, then I think I know what the distribution is. So that's the idea behind it. So we're going to say f of W, so the CDF of my random variable is just equal to 1 minus e to the negative lambda W. And this is actually the CDF of a very important distribution. So this is actually the cumulative distribution function for a very important continuous distribution. So this is the CDF for an exponential with a rate of lambda. There's only one parameter for the exponential distribution, and it's lambda for an exponential distribution. And let's go ahead and put in some more space here before we get to the example. And we're going to go ahead and define what the PMF is, right? So if I know, let me just write in exponential distribution. Lambda. So x is an exponential, this is how you'll see it written, exponential lambda. Then right now we know that so notice that I'm going from W's up here to X's, and that's fine. You can jump back and forth. So we know the CDF is f of x is equal to 1 minus e to the negative lambda x. All right, we get that from here. And then so this is CDF. And then we know we can find the PDF by just taking the derivative of this one. So the derivative, so f of x is equal to the derivative of this function here, f prime of x is equal to, let's see, the 1 goes away, the negative lambda comes down, so it's lambda e to the negative lambda x. So that's our PDF for this guy. If we want to find the expected value, so if you want to find the expected value of x, we would do the same thing that we talked about in the continuous distribution. We want to integrate over the entire, hold on. Let's write this thing out in its entirety. So draw, this is actually, if I'm going to include everything on it, so it's 1 minus e to the negative lambda x. And when is that true? That is true when, yeah, let's write it the other way. I'm going to start from when x is equal. So when x is less than 0, this thing's 0. When x is greater than or equal to 0, then it's 1 minus e to the negative lambda x. This one in its entirety is lambda e to the negative lambda x when x is greater than or equal to 0 and 0 otherwise. Okay. Now we want to do the expected value. So the expected value of my random variable x is just the integral. So I'm using this from negative infinity to infinity, but we know from negative infinity all the way up to 0, we get 0. And then so I'm going to start here at 0. So we're going to go 0 to infinity of x times f of x, which would be lambda e to the negative lambda x. And integration by parts, I'm not going to bore you with integration by parts. You would end up getting 1 over lambda. The variance of x, you would have to do the same integration by parts with a square term, with a square term instead of just a single x here, and you get something here, and then you put it back in the shortcut formula, we would end up getting 1 over lambda squared. Okay, if you wanted the standard deviation, so sigma would equal just 1 over lambda, right? You take the square root of the variance in order to get the standard deviation. This is equal to sigma squared. So the neat thing here is the expected value of the exponential distribution is the same as the variance. Okay, so let's go ahead and roll to number 2 here. So arrivals to Burger King drive-through arrive. So arrivals to a Burger King drive-through arrive according to a Poisson process with a rate of 400 per day. What's the probability that there are no arrivals in the next 5 minutes? Okay, so this one gives us an interesting way of doing it. I can do this 2 different ways, one being a Poisson and one being exponential. So let's do the exponential first. We'll do both of them. So exponential distribution. So let's do that. Let's let x be defined as, so it really depends on how you define your random variable. The time of the next arrival. So we'll let this be the time of the next arrival. And we'll do this in minutes. So just make it easy on us. And because this is a Poisson process, we've just shown that the next arrival arrives in accordance with an exponential distribution. So I know this guy is an exponential distribution with a rate. And so the rate here, we're going to have to, since let me delete all this garbage. So we know the rate is going to be what we're going to have to calculate here. Because I got it in terms of days here, but I'm trying to do minutes. So we can convert this 400 days. So let's go 400 customers per day, right? I'm going to use the chemistry way of doing business here, our little picket fence, if you will. And I know one day is 24 hours, and I know 1 hour is what, 60? Did I do? Oh, 60 minutes. Yeah, that's fine. Because we wanted in customers per minute. All right. So if we calculate this, 400 divided by 24, then divided by another 60. Give me a second. Is exponential 0.2778. Let me go ahead and write in what that stands for. That's in customers per minute, which is a little different than the 400 per day, but all we do is we converted it, so it's just a rate. And so let's use this distribution and calculate what the probability, right? So what probability statement would I write here then? I would just have the probability that x is greater than or equal to 5 is 1 minus the probability that x is less than or equal to 5, which is equal to 1 minus, now let's go back up and remember what the exponential distribution CDF was. So it's 1 minus e to the lambda, which that is lambda now, so negative 0.2778 times 5, which would be x in this case. Okay, so if we calculated that guy goes away. This turns into a plus, so it's e to the negative goes in, and we end up getting e to the negative, what was that, 1.8389, so the answer is 0.249. So that is our probability. So the 0.249 is the probability that given that x is an exponential distribution with this rate, that we wouldn't have 0 customers or the next one would come past 5 minutes. Okay, so the next one, so we should also be able to solve this using a Poisson process. So Poisson process. So what would that look like? So it would just be a different, so I'm going to use x again, but I'm going to define it differently. I'm going to say x now is the number of arrivals in the next 5 minutes. In the next 5 minutes. So 0, 5 minutes. And what are we trying to do there? We want this to be 0, right? So I want to, so if that's the case, and this is a Poisson process, then we know our random variable x is distributed as a Poisson alpha t, alpha being 400. So we need to do one of two things. So our 400 is customers per day, and this is in minutes. So we can either do, so since we've already converted days to minutes in our earlier one, I'm going to convert minutes to days. And so it'd be 400 times time. And we don't know what time is yet because we're going to convert our time to days. So what would that look like? So if I started off with 5 minutes, do our picket fence again, and then I know 1 hour is 60 minutes, so the minutes cancel, and I know 24 hours, what is that? So our hours cancel out, that's going to be 24 hours in 1 day. And that is, so the hours cancel out and it leaves me with days. So 5 divided by 60 divided by 24, that is 0.003472 days. And I'm taking it out to a bunch of decimal places here because I think we might need those decimal places later on. So what this becomes is x is Poisson 400 times my time now. So instead of 5 minutes, I got 0.003472 days, which is, if you multiply those out, you would get 1.389. All right, that is what we're going with. Okay, so what am I trying to show is that there are no arrivals. So what's the probability that x is equal to 0 is equal to alpha t, which would be 1.389 to the 0, e to the negative 1.389, all divided by 0 factorial. And guess what? E to the negative 1.389 is equal to 0.249, which is exactly the same as we got using the exponential distribution, which is right here. All right, that's all I got for this connection between the Poisson process and the exponential distribution. You need to understand the Poisson process and how these things are connected in order to be able to understand chapter 8. And so that's why I did this video. All right, that's all I got.